In this video, I will be explaining the topic of dimension reduction, and this topic comes under the unit model selection in our syllabus. So far, we have seen different types of methods for model selection. The first one was the subset selection, in which we have we have seen three different methods or the algorithms for subset selection. In case of the subset selection, we enumerate 2 to the power of p different models, where the p is the number of variables or number of features. And in case of the p features, there are 2 to the power of p models are there, and out of 2 to the power of p models, we select only one model. And that selection process is carried out in three different ways. The first one is called as the best subset selection. The second method is called as the forward stepwise refinement. And third method is known as the backward stepwise refinement. In case of the shrinkage is also a kind of model selection method, in which if there are if p features are there, now here we are not selecting features, but here we are making if the model is y equal to x1 beta 1 plus x2 beta 2 plus xn beta n plus beta 0. Sorry, here p is the number of variables, so xp beta p. Then in this case, the beta values for insignificant features or the irrelevant features, it is made 0 or near to 0 in case of the shrinkage. And I have explained two different shrinkage method. One is called as the ridge regression, and second one is called as the lasso regression. Now in this lecture, I will be explaining principal component analysis, which is one of the method for dimension reduction. In case of the dimension reduction, now we are going to reduce the number of features, if there are p features, from to the number of m features, where the m is less than p. So that is called as the dimension reduction. Now here I would like to explain what does it mean by dimension reduction and how it works, by giving one very common example which helps you to develop the intuition behind the dimension reduction method. Let us consider the task of predicting end semester examination mark, and now here I am using more number of features. There are 5 features I am using. The first feature I am labeling it as the quiz 1, second feature quiz 2, third feature is quiz 3, fourth feature is quiz 4, fifth feature is the MSc and or mid semester examination marks. And out of those 5 features, I would like to predict the value of output variable or y, that is the end semester examination mark. Here the p is equal to 5, that is the number of features. And now when the number of features are very large, it may we may get the model accuracy will be more, but sometimes the model interpretability gets reduced. So to avoid that problem, what we are going to do is that we are going to reduce the number of features from 5 to some other features like 3, 4 or 2. So here suppose that I have replaced this quiz 1, quiz 2, quiz 3, quiz 4 and mid semester examination. If I have added all these marks together and called them it as one variable, that is called as the internal assessment, then the problem will become the one dimensional one or simple linear regression. Earlier it was the multiple linear regression problem. Now internal assessment, here I am labeling it as the quiz 1, quiz 2, quiz 3, quiz 4 and here I have added all together. So here what I am doing is that I am adding or combining the features. Here I am combining the 5 features to make it only one features. And this IA is equal to quiz 1, quiz 2, quiz 3. So this is the linear combination of features. So the principal component analysis or the dimension reduction, the purpose of the dimension reduction is to identify smaller number of features or to map the given p features into the m features where the m is less than the p, and model the regression problem in terms of the reduced um set of features. Now here in this slide I am developing more formal way of defining the dimensional reduction problem. In case of the conventional approach, we are predicting the value of y in terms of input variables or the independent variables or the input features. There are p features are there, and here beta 0, beta 1, beta 2 to the power beta are the linear coefficients, plus this is the irreducible error. The same thing can be expressed in this way. Now in case of the dimension reduction problem, the linear regression or the y output variable is now expressed in terms of z1, z2, zm, where zm, z2, zm are transformed features, and this m, the number of m is less than the number of original p, that is less than p, and this z is the linear combination of our original p predictor. Linear combination means that suppose that z1 may be a combination of x1 plus x2. So this is the linear combination, and such types of combinations are not allowed where this is the quadratic combination. This is the linear combination. So Z1, Z1 here, which is the transformed feature expressed in terms of the input original input features, is a linear combination of the mm, input features. So now this Zm is the, and this phi jm is some linear coefficient, and Zm is the ith number of transformed feature like the Z1, and this transformed feature is known as the components. And now the linear regression problem is expressed in terms of this Z1 and not this X1. Now Y is expressed as the theta 0 plus m to the power of m from m to m. M is less than p here, and theta m z I m. Now here our purpose is to linear regression. The objective of the linear regression is to identify these coefficient called the theta 0 to theta m, and here the I is equal to 1 to n. N is the size of data. If there are 100 records are there, then the n takes the value of 100. So now the when you are adopting a principal dimension reduction approach for solving the regression or the regression problem, then that works in two stages. In the first stage, you need to identify a linear combination of components, and then you need to express or solve the regression problem for those components instead of the original input vectors. Now here I am explaining the principal component analysis with an example. Let us consider prediction of sales from the population and advertising budget. Now here the number of features, that is the P, is equal to 2, and these features, input features, are the population and ad spending. Now, and our objective is to predict the sales volume from the population is one input feature, and another input feature is the advertising budget. And now consider that this population is expressed in terms of the hundreds, thousands here, means 10 means 10,000, 20 means 20,000, 30 means 30,000. And here also this figure represents in the thousands, it means rupees spent on a advertising budget like 10,000, 15,000, 30, 20,000 like that. And this is the scalar plot for the population versus the ads plot, where the these dots represents the sales volume. Now, here I am showing you, I have not we have defined the principal components or the components of a input features are the linear combination of input feature. The components are nothing but the linear combinations of the input features. And here I am showing in this figure, there are two different components. This one is the first component and this is the second component, which are perpendicular to each other. And this component here Z1, now I am expressing in terms of this equation like 0.839 star pop minus pop bar. Pop here means the population and pop bar means the average of the population value, and 0.544, these are nothing but our phi, and ad means advertising budget and ad bar means the mean of the advertising budget. And Z1 is one component, and this Z1 is the component, means it is the linear combination of the input features. Here the input features are the population and the advertising budget. Similarly, there is another component is present which is called the Z2. Now suppose that this is the Z1 and this is the Z2. The Z2 is now the combination of 0.54. Here only the coefficients are changing. Uh, Here this is the phi 1 and this is the phi 2, and here the phi 1 is this and this is the phi 2. So phi 1 values and the phi 2 values are the interchange here. So this is the second component. If in your data set there are p number of features are there, then there are p numbers of components are there. P components are there. Here because there are two features are there. That's why there are here are two components are there. The first component here I am calling it as the principal component, and the second component here I am calling it as the second component or the Z2. These components are nothing but the linear combination of the input features, and the number of components in a particular data sets are always equal to the number of features in your data sets. If there are p features are there, then p components are there. Now see here, when I plotted the population data against the population data against the first principal component and the second principal component, I will get two different scalar plots. So this is the first scalar plot in which the relationship between the first principal component and the population component is very strongly defined. See here. Whereas in case of the second principal component, the number of the variation is weakly defined. So our purpose is to reduce the number of features. See, there are two features are there, and here we got the two principal components are there. Now out of these two components, we need to select only one component, and we can select a component which is showing very strong relationship with the input features, because here the first principal component is showing the strong relationship with the first feature. That's why we have selected the first principal component. And here the weak relationship is there, or there is no relationship is present between the second principal component and the population. So we will discard this second component. Similarly, for advertisement budget, if we plot a scatter plot of first principal component versus the ad spending, we get this kind of graph in which the relationship between the first principal component and this advertising budget is a stronger one. Whereas in case of the second, second principal component versus the uh, ad spending. This relationship is a very weak, and this is the strong. So we will neglect this and we will select this. So in the previous case also, this relationship is the strong relationship and this is the weak correlation, and that's why we have neglected this. So here now we have selected only one component, that is the first component or the Z1, and the Z1 is expressed is a linear combination of, this is the equation for the Z1. So here the Z1 is the linear combination of two input features. Now these two input features are transformed into one single component, that is the Z1. So now the number of features are reduced from two to one, two dimensional to the one dimensional. Earlier there was two variables were there, the population and the ad spending, and which are now replaced with the values of Z1. And how values of Z1s are calculated? By solving this equation, the values of Z1 are calculated. We have not seen how these values are calculated, phi1 and phi2. We will see that how the principal components are calculated. Here I have defined that a linear a principal component is nothing but the which is the linear combination of input features. If there are p number of input features are there, then p components will be there in your data set, for your data set. And out of those p components, our purpose is to select a component showing a high degree of correlation between the component and the input feature. That component is selected. Now here I will be explaining how to calculate the principal components. And for calculating the principal components, we need to know how to calculate the mean. This is the formula to calculate the mean or the average value. And xi is our input feature. And this is the way in which you calculate the covariance. Covariance is always calculated between two features. X and y are the two features, and this is the formula to calculate the covariance, which is the nothing but the x minus x bar. So x, here the x bar is the mean value. The mean value is calculated like this. So these values we need to know, these formulas. Then one of the central concept in calculating the principal component is what does it, we need to know what does it mean by eigenvalues and the eigenvectors. So eigenvalues and eigenvectors are related to the square matrix. So the square matrix always have eigenvalues and the eigenvectors. So here I am showing a matrix multiplication. This is calling it, I am calling it as the A matrix. So this second matrix is, I am calling it as the vector because this is the one dimensional one, and this is the resultant, this is the product P. Now in this case, this is when you multiply A matrix, that is the 2 3 2 1 by 1 1 and 3 value, you will get this result. And this result you cannot express as another, this matrix you cannot represent as a multiplication of a scalar and the another matrix. See here, in case of the second matrix, that is the same matrix A, and the vector here is the 3 by 2, 3 and 2. When you multiply 2 3 and 2 1 by 3 2, you get this result 12 8. And now this 12 8 can be represented as a scalar. This 4 is the scalar, this is not a vector, and this is the vector. If you can represent the product in like this, scalar multiple times the vector, then that is called as the eigenvalues and the eigenvector. So now here the 4 is the eigenvalue and 3 2 is the eigenvector. When you multiply a matrix with another vector and the product of that multiplication can be represented as a product of scalar and the vector, then it is called as that the matrix is called that it has eigenvalues and the eigenvectors. Eigenvalue is the scalar and eigenvector is the vector by which you have multiplied the given matrix. So this is the definition of the eigenvector and the eigenvalues. So these are useful, these are required in order to calculate, in order to find the principal components. Now, the method to calculate the principal component is like this. First, get some data, then subtract the mean from each and every data observation or data point, calculate the covariance matrix, calculate the eigenvectors and the eigenvalues of the covariance matrix, choose the components and forming a feature vector, and derive the new data sets. So we will see how it works. Now we are going to use Python libraries to find the covariance matrix and to find the eigenvalues and the eigenvectors. We are not calculating it manually, but we are making use of the mathematical libraries that are provided by certain programming languages like R or the Python. And in order to, if you are using the Python, then you need to import the libraries like array, mean, covariance, and EIG stands for the ion. And this module calculates the ion values and the ion vectors. And you can carry out all these steps in one single statement if you import a PCA library from the Skylar Python library. So I will be explaining the both methods here. So now let us consider. So this is the data set that we have given. Here there are two components, two vectors are there. This is the first vector x and this is the second vector y. So these are two vector problem is there. P is equal to 2 and now we are going to reduce it equal to P equal to 1. And here we need to identify some equation of for component z1 in terms of the x and y. In terms of the x and y, we are calling it as the, which is the linear combination of x and y, and we are calling it as the component. So this is the way in which you define an array in the Python. So this is the same data is implemented as a Python statement to define it as the array, two-dimensional array. It has 10 arrows, 10 rows and 2 columns. Now, if you want to calculate the mean in the Python, you can calculate mean by this method. And here mean is, the mean value is subtracted from the given input feature, input array a minus mean. So print C. So this is the second step, subtract the mean. Once you have loaded the data into the memory, you need to identify the mean for the input feature and subtract that mean from the individual observations. Now this value 6.9 is the subtraction of 2.5 minus 1.81. So 1.81 here it is the x mean and this is the y mean. And similarly 0.49 is the subtraction of 2.4 minus 1.91. So this is the y bar. Like this you need to do for each and every observation, that is the 10. So this can be done with by this method or by this statement. C equal to a minus m and print C. So this is my C. Now once you got the subtracted the mean value from all the data observation, you need to find the covariance for that. And this is the covariance matrix for the, if there are the xy for a covariance matrix for two features, the size is a square matrix of 2 by 2. If in case of the p features, the size of this covariance matrix is always p by p. So this is the covariance matrix that I have got by executing this method. Now once you got the covariance matrix, next step you need to calculate the eigenvectors and the eigenvalues. And the eigenvalues and the eigenvectors are can be calculated by EIG method from the Python library. V is my covariance matrix and you will get values and the vectors as the output. And these are the vectors. So this is the first vector or V1 and this is the second vector. and this is the ion value or EV1, and this is the EV2. It is usually then these are arranged according, these vectors are arranged according to the highest to the lowest ion value. Here the highest ion value is 1.28 and 0.04. So now the first component will become, this is the first component and this is the second component. So like this ion values are arranged according to the descending order, and the highest and corresponding ion vectors are also organized. So this is the first vector, this is the second, and now this is called as the first component. Highest one is called as the first component. Second highest is called the second component. Third highest is called as the third component. Like this. Now once you got the principal components, you need to transform the data now. So now this is the transformation of the data. So here, because this is the Z1 and this is the Z2, or this is the first component and this is the second component. And like that, we got the two components. That's why we need to select out of those two few components. That is the, here we are going to select only one component, and that component is selected for which the ion value is the highest one. In case of here, the ion value is the highest one for the this Z1 or the second vector. The second vector, the ion value is the highest. So that's why we have selected that and we are labeling it as the PC1. In another way, the PC1 now can be represented by this equation, which I am calling it as the PC1 equal to minus 0.677. Why I am taking the minus 0.677? Because the minus 0.677 is my first value in the second vector, and this is the second value. See, 7.34. And here the x means the original input feature, x bar means the mean for the x, y means the second input feature, and this is the mean value. Now the PC1 is the linear combination of this. Here the two-dimensional vector is reduced to the single dimensional one. Earlier the size of the vector was the 10 by 2. Now it is the size of the vector is the 10 by 1. So this is called as the dimension reduction. Now once you reduce this dimension reduction, then you can perform the regression problem using this Z1 as your input feature and develop a model of regression model for the Z1. Now the regression model that you have built from the principal component will give you better performance in terms of test MSE or test mean square error. Now here on this slide I am explaining how the PCR means principal component regression, a regression carried out using the principal component analysis method, that is called as the PCR. The performance of the PCR in terms of number of different components, here I am on this slide is shown. This is a simulated database in which there are 45 number of features are there. See, the number of features are very large and the data size is very small, that is the 50. Now means that the number of features, data size is approximately equal to the number of features. Sometimes it may happen that the number data size is less than the number of features. So in that case, the principal component regression is typically used. And here, see, this graph shows you the number of components. Means if here in this case, in this particular case, there are 45 features are there. So that's why there will be the 45 components will be there. And the 45 components, if you are modeling a regression using the 45 components for a 45 number of features, it is as good as the same. You are not reducing any number of features. So if you use less number of features and go on increasing the number of features, how the model performance varies. So that is studied, illustrated with this graph. If you observe that as the number of components, here the number of components is plotted on the x-axis and the mean square error is plotted on the y-axis. This graph, this first line or A, is the squared bias. Uh, See, or the error or the RSS, we call it as the RSS. So RSS gets reduced and then it becomes the standard one, or constant one, as the number of features increases. For the smaller number of features, like for example, if only you are 5 features you are using, so the 5 number of features, the error is high. But as you go on increasing the number of components, then our number of features, then the error remains constant. At the same time, variance is also very high, then it suddenly drops and then it becomes starts on increasing. And see here, when you use the reduced number of components, your variance, your bias is very high, but the variance is you will get the low variance. What does it mean by? It means that your model will perform better on the test data than as compared on the training data. Means that your model will not be suffering from overfitting situation. So in order to avoid the overfitting or high variance situation, we typically use the principal component analysis by reducing the number of features and expressing number of features in terms of components. Components is nothing but the linear combination of the input features. And when you do that, you will get a test. You will get the better performance on error or the bias for test data as compared to the training data. So this is about the principal component analysis. Thank you.